Hello. Today we're going to look at how to find the area between two curves. That's going to be the topic for today. Okay, so we're looking at some sort of scenario like this. We have two functions here, functions of x, f of x and g of x. And between two values of the x, the a and the b, we're going to find the area enclosed between those two curves. Okay, so that's the basic setup. And we can leap straight into the theorem. So we'll assume that f of x and g of x are continuous functions and that they're defined in that region a to b. We'll also, for the sake of this, assume that the f of x is greater than or equal to the g of x for all x in that region. Then the area of the region bounded by the f of x, the g of x, and those lines a and b, x equals a and x equals b, is given by this formula. Okay, so we integrate from a to b, and we have f of x minus g of x, in other words, the higher one minus the lower one. And that's about it for the theorem, actually. It's not too bad. Let's say it was just a question of finding which one is higher and subtracting which one is lower. Just going back to our picture, we'll notice here both of the functions are above the x-axis. That actually doesn't matter if they're both below the x-axis, or one's above and one's below, or they switch at various points in time. It's still this function, this theorem, which says it's the f of x minus the g of x. Okay, so with that formula in mind, let's leap straight on to an example. Okay, so we're going to find the area between minus 2x squared plus 4x plus 1 and 4x cubed minus 10x squared plus 4x minus 2. And we're going to do that from x equals 0 to 2. Now, in all of these cases, it seems like a good idea to actually take a little look at a picture. In particular, it'll help us find which one is a higher function, which one's a lower function, but it might also help us see anything interesting that's happening. Okay, so we have a very detailed picture here, and this shows us that the f of x is the higher function and the g of x is the lower function. We can see obviously that these two functions are continuous on that region from 0 to 2. And given that that's true, this is very straightforward. Okay, so we just repeat the question. So we take the integral from 0 to 2. We take the f of x to be the higher function, so that's the first one, and then we subtract the g of x to the lower function. And that's about it. I mean, it's very simple. These are polynomials, obviously, so it's a very straightforward integral. So I won't put in all the steps here, but we can simplify and integrate, and that becomes 34 over 3. And that's about it, really. Okay, let's take another example. Slightly different, but not a lot. This time we've got the area enclosed by two functions. Okay, and until we draw the picture, it might not be clear exactly what this means. But right now we're saying that the area is enclosed by these two functions, x squared minus 5.5x minus 14 and 1/2 x plus 2. And so I say, we really need to draw a picture just to see what's going on. Okay, so here's our picture. So obviously the 1/2 x plus 2 is the linear function, and the x squared minus 5.5 x minus 14 is the quadratic here. And this shows us that there is an area enclosed. Okay, the two functions meet here and here, and so this encloses an area. Okay, so this graph tells us that the g of x in this case is the higher function, the f of x is the lower function. Also what the graph gives us, and we can find this other ways, is what are our limits of integration going to be? Okay, in this case we can see that this goes from -2 to 8. And since these meet at these 2 points, that's going to be our limits of integration. Now note, of course, this graph's very accurate. If we want to find that algebraically, we just set the two functions equal to each other and solve that for, in that case, 2 values for x. We'd use the quadratic formula to find the 2 values of x. But sure enough, we found that the two x values are -2 and 8. And therefore our integral, so we'll restate the question here, our limits of integration are -2 to 8. As we saw, the g of x was the higher function and the f of x was the lower function, therefore we subtract in this way. And again, that's our integral. When we actually get to this point where we have the integral, that's very straightforward. It's just polynomials. And so we integrate, we get 500 over 3. And that's about it for that. So as I say, just going back a step, make sure you draw a picture and you can see clearly what's going on. It'll also help you find the limits, although setting them equal to each other to find the limits is a good idea as well. Okay, so let's take our final example, and this will be a little bit trickier. Okay, so we've got the area enclosed by, in this case, 3 functions. So we have y equals x squared plus 1, y equals 1/4 x minus 3 quantity squared plus 1, and y equals 1. And once again, we certainly need a picture here to see what's going on. So those are our three functions. Okay, the y equals 1 obviously is the horizontal line. The y equals x squared plus 1 is the parabola to the left, and then we have another parabola over to the right here. Okay, and we want the area enclosed by that. And always we've said so far that we want to take the higher function minus the lower function, but it's not quite clear what that means here. I guess we could probably do that, but it would probably involve breaking this in two. Okay, so we sort of chop this in half here. On the left-hand side of this line, we're below this x squared plus 1, whereas on the right-hand side of the line, we're below this other function, and in both cases, we're above 1. So we could probably break it in two and do two integrals, I suppose. That'd be okay, but it seems a bit cumbersome. And that's because always when we've been doing these things, we've been thinking about it vertically. Okay, but clearly we can also think about it horizontally. Okay, we're only concerned about the area. It's still the same area we think horizontally. But if we're thinking horizontally, instead of being constrained between sort of two different functions and this y equals 1, we're just constrained between this higher function and this lower function. Okay, our limits, we go from 1 to 2. We're below this, we're above this. And that would be our integral. And that's great, the only problem being that our functions are y's in terms of x, and if we're going to think horizontally, we need to think x's in terms of y's. So we can certainly do that, and in fact we'll do that right here. Okay, so if we've got y's in terms of x's, we need x's in terms of y's. So of course that means taking the inverse of each function. We do need to be a little careful here with the squares. When we take the square roots, we need to be careful to think about which is a positive or negative square root in which particular section of the graph we're in. But these are the functions we need. So instead of taking the y's in terms of x's, we take the x's in terms of y's. And now maybe if we just bring in the graph here, we can see that this function is the higher, this function is the lower. Therefore, we're going to do this one minus this one. And again, we can just about see we're going to go from 1 to 2 because now the y values go from 1 to 2. And I guess we've said this in all three of our examples now. When we get to the actual integration stage, this is pretty straightforward. Okay, it's a little bit of chain rule because of the square root here, but it's a very straightforward integral. It's obviously dy rather than dx, but we can integrate this, and in fact it turns out that the area in there is 1. So as I say, the theory here is pretty straightforward. It's just a question of applying it, finding the regions we're interested in, and integrating. And that's about it.